Hello and welcome to this tutorial on the link state routing protocols. Now, the link state routing protocols are a lot more complex than the distance vectors. So if you've watched that tutorial already, you're in for something a bit more complicated. However, this complexity delivers a lot more benefits than the distance vectors. First of all, link states are much faster when it comes to convergence. Second, the link state protocols offer better loop avoidance than the distance vectors. So all of those features that we talked about in the distance vectors, the split horizon, the hold down timers, well, we're not going to have to cover as many features in the link states because they are just designed differently and they inherently address these issues much better than the distance vectors. Two examples of a link state routing protocol are OSPF and ISIS. Now, for the CCNA studies, you need to know OSPF, but they don't really focus on ISIS. So we're going to go ahead and discuss the basic characteristics and features of the link state routing protocols. And we're going to do that, though, in the context of OSPF, because later on we're going to have to talk about OSPF anyway and learn all of those details. So this will fit in nicely. Okay? Okay, let's start with an overview, and then we'll drill down into each area with some more detail. So to start off, link state routing protocols need to form neighbors just like the distance vectors. However, a crucial difference is, with a link state routing protocol, a router can form a neighborship, or what is sometimes referred to as an adjacency. It's just means that they are full neighbors with routers that are not directly connected to them. So router B and C could become neighbors if they're both running the same link state routing protocol. There are a lot of details that dictate whether or not they can, but generally speaking, it's possible. Whereas distance vectors, router B could only become a neighbor with A and D. Okay, so once they do form neighbors, then each router has to advertise some information about itself. And these advertisements are called LSAs. That stands for link state advertisement. And inside the link state advertisement is some information about the router itself, all of the connected links to the router, and what state those links are in. And that's actually where the name comes from, a link state routing protocol, because that's one of the factors that is included with this protocol when they talk to each other. So each router will start advertising information, it'll start sending out these LSAs, and what happens is every router is going to receive the LSAs from every other router on the network. That means every router is going to learn the same information about the entire network. We're no longer stuck with only hearing information from your directly connected neighbors. Now routers B and C will receive information between each other, and they take all of that information and they store it in a database. This is commonly referred to as a topological or a link state database. So every router is going to have the same information in their database. That's a crucial difference here when compared to the distance vectors. Now, after this database is built, each router is going to run an algorithm on the data in the database. And the result is they then create their routes, the best routes to each destination. And once that's done, those routes are put into the routing table. So that is an overview of how link states work. Let's take a look at how neighbors are formed and take a closer look at those advertisements, the LSAs between them. So how do routers running link state routing protocols become neighbors? Well, they basically try to discover other potential neighbors on the network. And so with OSPF, a router will send out something called a hello message. And it'll send it out, and any routers that receive it who are also running OSPF could respond. And so let's say routers A and B are both potential neighbors, and they're both sending out these hello messages, which contain some information about each other. They just won't immediately become neighbors. With OSPF, they're going to check each other out first. They're going to compare their configurations, and they do that to make sure that they should become neighbors, because there are some instances that we'll cover more closely in the OSPF tutorial where they should not become neighbors or they cannot become neighbors. Okay, so there's a bit of a vetting process that goes on first. Now, if it turns out that A and B should become neighbors, and then they actually do become neighbors, only then can they start to exchange the link state advertisements. Okay, so if you're not a neighbor, you won't share your local information. They will not exchange advertisements, only after you become a neighbor. Now, this process of sending out the link state advertisements is often referred to as flooding, and you'll hear that term a lot. All that means is that each router is going to make sure that all of its neighbors get an LSA. Now, when a router receives an LSA, let's say router B sources one and router A receives it, router A is going to immediately turn around and forward it to all of the other neighbors. So that way we can make sure that at the end of the day, all of the routers are going to receive all of the possible information about the network from all of the possible neighbors out there. So we mentioned earlier that each router ends up with the exact same information. Well, this is how it's done. Now, these LSAs are going to be sent out periodically, otherwise they'll time out. So OSPF will default to every 30 minutes. So this is a refresher of sorts. So router B, every 30 minutes, for some of the LSAs, it's going to send them out again. And router A will receive them, and by doing that, it'll know that that information is still current, it's still fresh. Keep in mind, a big difference between a link state and a distance vector is that when router B sends out that 30-minute periodic update, it's not sending the entire link state database at once. Rather, it's just going to send a little bit of it. So it staggers those advertisements, so it's not sending a huge amount of traffic all at once every 30 minutes. So the link states are kind of smart about how they do this. Now, even though this periodic refreshing is happening all the time, if a change occurs on the network, a failure or an addition of any kind, then updates can be sent out immediately. They don't have to wait for that interval to come about. And this is just default behavior for a link state routing protocol. Now, once each router has a full link state database, and it's the same as all of the other routers on the network, it needs to go ahead and actually do something with that information. So what happens is it'll apply an algorithm, the shortest path algorithm, to that information. And that process is going to return some routes, the best routes that it knows about to get to each destination. And with OSPF, the metric that we talk about is called cost. And this metric, this cost, is based on bandwidth. And it's pretty simple. The higher the bandwidth, the lower the metric, and that's the one that is more favorable. So for instance, if router B is trying to determine a route to a network that router C knows about, it can get there from router A, or it can get there by going through router D. Well, router A has a fast Ethernet link between it and router B and it and router C. However, router B has a gigabit Ethernet link to router D, and then D has a fast Ethernet to router C. So it's likely here that router B would choose the route to get to a network off of C by going through router D. Now, once these calculations occur, then those routes are put into the OSPF routing table. Okay, so the information in the link state database, that is not a route. That's just information about all of the links on the network. Only after the algorithm is applied to that information are the routes then created. Now, when a network change occurs, let's say the link between routers C and D fails, the connected routers are going to immediately send out an updated LSA with this failed link information. So routers A and B are each going to receive the updated LSA, and then they'll update their link state database, and then they'll go ahead and rerun the algorithm on this new data. And they'll do this in order to determine if a new, better path now exists because of this failure. And so they'll run the algorithm, they'll come up with a new path if one is available, and then they'll update the route table with this new information. So then router B, for instance, could then determine, okay, I can now successfully route to a network behind router C by going through router A, since this link over here has now failed. Again, keep in mind, LSAs are just information about the network. The routes are created after the algorithm is run. Okay, so to summarize what we covered, we now know that the link state routing protocols use LSAs in order to exchange information between routers. And this information is stored in a local database. And at the end of the day, each router is going to have the same information in their local databases. They all see the same network. Now, each router is going to apply the algorithm to their link state database in order to generate their routes, in order to determine the best path to each destination. And then those routes will be put into that routing protocol's route table. Now, one of the biggest benefits of using a link state over a distance vector is that the link states have a much more rapid convergence time. They also handle loops a lot better as well. Okay, so that's it. That is the link state routing protocol tutorial. Be sure now to follow this one up with the OSPF tutorials, because that's where we jump into all of the details on how OSPF works. Okay, thanks for watching.